with I'll state a theorem of Beauville and Voisin. And so this is about projective K3s. So everything will be over C. Okay. And so the theorem states that there exists a special zero cycle of degree 1. So a rational equivalence class of zero cycle. So an element of Chow 0 of x such that the following two facts hold. The first fact is that if you intersect any two divisors on x in the Chow group, in the Chow ring, you will get a multiple of this class. So these are what I would call decomposable zero cycles, so meaning the intersection of two divisors on a surface. And the first fact is that this is a multiple of this class, and there's a similar result saying that the second Chern class, of course, in Chow 0 is a multiple of this class. Okay, and so let's stop for a moment and look at property number 1. And so on one hand, this is slightly surprising because the group Chow 0 of a smooth projective surface with strictly positive geometric genus is huge. So 1 is sort of surprising because Chow naught of x is huge, as was mentioned in Voisin's talk of yesterday, because PG is strictly bigger than 0. So Mumford showed that this, even if you look at zero cycles, of course everything is modulo rational equivalence. Even if you look at zero cycles of degree 0, right, you cannot parameterize in any reasonable way this group by an algebraic variety. Okay, so in that sense it's huge. Should think it's like infinite dimensional, but strangely it's sort of weird that any intersection of two divisors is a multiple of this fixed class. On the other hand, the proof, I can show you the proof. It's rather brief. So proof, you have to use a result by, I think it's usually associated to Bogomolov-Mumford, which says that in any complete linear system on a K3 surface, you will find a divisor which is made up of rational curves. So use theorem of, I think, Bogomolov and Mumford, which says that on any complete linear system, any complete linear system on X, so X is always a projective K3, contains a divisor supported on rational curves. So now once you know this, you notice that you can give a well-defined zero cycle up to rational equivalence of degree 1. You can define it this way. It follows that, I'll just make a picture. If you have 2 points on X and both lie on rational curves, then they are rationally equivalent. So these are rational. Then it follows that these 2 points are rationally equivalent, because take an ample divisor on X, and there is in the complete linear system given by that ample divisor, there is a divisor supported on rational curves. So that will be something supported on rational curves that you can use to go from P to Q through rational curves. Okay, so that will tell you that the class in Chow 0 of X of P contained in a rational curve in X is independent of P. Any 2 such P are rational equivalent, and so O of X by definition is the class of any point on a rational curve. And then from this, once you have defined OX this way, this equality is immediate, because you write D1 as the difference between, say, 2 ample divisors, which are represented by rational curves. Similarly for this, and so you break up the intersection as a sum of multiples of P. Okay, and so that's the proof of this. Now, so I'll comment on the second equality later. So now so a natural question that you might ask is, given a projective, smooth projective surface, let's say, what is the rank of the group of decomposable zero cycles? So decomposable zero cycle is the zero cycle which can be written as an intersection of 2 divisors. So the rank of the group of decomposable zero cycles. Okay. And no, I guess you're right. If the surface is regular, then it's okay. But yeah, if the surface is regular, then it's otherwise. Yes, you'll have something. You're right. It will be infinite. Let's say. So then the question makes sense. Okay. Yeah. Otherwise, it will be possibly infinite dimensional if it's irregular. Yeah. Okay. And so there is one answer is that it. Yeah. So we'll just thinking of regular surfaces. So one answer is that it can certainly be as large as you want, and you can just start with you start with a surface with P. Okay, let's say regular, and then you pick n very general points on Y then sort of the proof of Mumford's theorem about zero cycles will tell you that there is no non-trivial linear rational equivalence relation between these points. Okay? And so then if you just blow up this surface at these endpoints and you take the self-intersections of the exceptional divisors, you will get decomposable zero cycles which have no, and decomposable zero cycles which have no relation. Okay? By Mumford, no non-trivial relation, like K1. Then you take the blow up at these points of y and take, E1 squared independent decomposable zero cycles. Okay? So that's pretty easy. And so, but what about, so you might ask yourself, what about a more natural class of, so less artificial class of examples like, for example, surfaces, smooth surfaces in P3. So, okay. So, Li Fu showed that there exists X of degree 8 such that set of let's call them decomposable cycles. I won't use it, but let's say has rank at least 2. Okay? As you would expect. I mean, as I said, that property is surprising. Only it's not. Okay, and so let me state what one can prove. Okay, so maybe I can put my name here. Okay, so now I want to produce more examples with large rank. So, of course, if I want if I want the group of decomposable zero cycles to be, to have large rank, the Picard group of X should have large rank. Otherwise, there's not much. So I fix n smooth curves in P3, pairwise disjoint. And I'll look at surfaces which contain those curves, and I'll take the self-intersection of those curves. Okay, so smooth pairwise disjoint curves, integral curves. Okay, and I want one condition on the curves is that such that for all the indices, the canonical of the curve, even up to torsion, is not the restriction of a line bundle on P3. Okay, that's it for there does not exist. So now the Chow groups will always be with rational coefficients. Okay, let me just say that so I don't have to Whoa. Okay. That's always the case. With Q coefficients. Okay. Okay. So I'll assume that the canonical of each of these curves is not, even up to multiples, is not the restriction. So such that well, okay. So I don't want them to be. So these have to have at least genus 2. So certainly if you can't choose them rational or of genus 1. So I assume that we have these pairwise disjoint smooth irreducible curves. Then if D is one can make this effective, but I haven't made it. If you choose a degree which is large enough and you choose a surface, a very general or smooth surface, so it's it has to contain all these curves. I want to be smooth because I have to do intersections. Then if you look at so this is the hyperplane class on X, on the surface, are linearly independent. Okay. So how does one prove this? Okay. Yes. Okay. I wanted to make one remark. So as I said, of course, if you want the rank of the group of decomposable cycles to be large, you need the Picard group of X to be can't be too small. But that certainly is not enough. I mean, large rank. Chow 1 of X must be large, but certainly that is not enough. So there are, say, many examples of surfaces whose Picard group has large rank, but whose Picard group up to torsion is generated by lines, for example. And so for those examples, you will get something. You'll get exactly this. Well, large rank generated maybe up to Q by lines. Okay, so for those, certainly that will. Okay. Pardon? because then, you know, you have, when you intersect any two divisors, it's sort of like intersecting lines. So you always, I mean, as far as you connect, if you can connect any two lines by an ample divisor, which is rational equivalent to a sum of lines, then no, you're right, but so yes, yes, okay, okay, that's more, yeah, that's what I have to avoid here with this condition. Yeah. Okay, that's easier. Yeah. Okay. In fact, I was going to get to that point. Okay, and in fact, that's the next step. Okay. So before giving you an idea of how one proves this, let's exactly see what this relation that Claire was talking about. So relations between. So this will explain why one needs this condition, and also, okay. So so I have this. Should I? Well, maybe I'll introduce some notation. Maybe I'll use it. Okay. So this is a hyperplane class on P3, and I have my smooth surface. Okay. And capital H is the hyperplane class on X. Okay. And I have a curve on X. Okay. So first relation that I get is that the degree of X times C dot H is equal to the degree of C times H dot H. Okay. And so why is this? Well, so let me see, what is my notation. So let's call I the inclusion of X in P3, and I want J is the inclusion of the curve in P3. Okay. And so what do I want to do? I want to push forward C to P3 and then pull it back to X. Okay. And then what I get, this is C dot C1 of the normal of X in P3, right? And so this is this term here, right? Okay. But on the other hand, the push forward of C, this is rational. I mean, this is the same class as the degree of C times H squared, small h dot small h. Okay, it's a class in P3. And so if I pull it back to the surface, I get, right? So this is the degree of C times H dot H. Okay. So what? So now I think that I have one curve and H. A priori, I have three decomposable zero cycles I produce: H dot H, C dot H, and C dot C. And one of them is redundant. So, I mean, C dot H I can sort of eliminate if you want. And now there is another relation that holds if the canonical of the curve is induced from the ambient, okay, just by the adjunction formula, okay. So now suppose that the the dualizing sheaf of C is A H to C, okay. Adjunction. So if you write adjunction on the surface, will give you that C dot C is equal to C dot A plus 4 minus 2H. Well, maybe. Okay. So conclusion, the rank of this subgroup is at most 2 and equal to 1 if the canonical of, let me write it, okay. Okay. So that explains why I want to rule out this case, at least. At least it explains why I want to rule out this. Okay. And so how does the proof go? So maybe I can erase this. So I have these curves. So they are smooth, pairwise disjoint integral curves. Okay, and so I blow up P3 with center the union of these curves. Okay. Maybe I can call C is the union. Okay, and E is the exceptional divisor. Okay, and I assume, okay, so let's say D is the degree of X of the surfaces that we are. Okay, so I want to assume that D times the pullback of H minus E, say, is very ample. So these will be given, the sections of these will be given exactly by degree D surfaces containing C. So that's the relation with that. And I want to consider the universal such surface, but instead of looking at it in P3, I look at the blow up in here, okay, which will be generically just the same thing. Okay, so I look at the universal surface. So so this will be the couples XS. So this will be in the product of W times this linear system. And the condition is simply that X is in S. Okay. So this is the family of surfaces parameterized by the linear system of degree D surfaces through C. But we are looking at the blow up of these surfaces in W. So generically you get just the same surface, but if it's single along C, you will get something different. Okay, and so what we have is maybe okay, so we have two projections. And maybe I should give names to these. Okay. Okay. Okay, and so this is a nice p whatever fibration, because I'm assuming that this is very ample, so there's no problem. I mean, base point 3 would be enough. And so this is smooth, of course, if you look at this vibration. Okay. And so what I want to do is sort of typical. I want to ask myself, let's assume that for all surfaces containing of degree d containing these curves, there is a linear relation among these zero cycles. Okay, then the sort of, I think what it's called, the spreading principle tells me that I will get a relation among codimension 2 cycles on this universal surface. And so I want to get a contradiction from that. Okay, so so now, of course, if you look at the various components of the exceptional divisor lying over the C1, C2, and Cn's, if you take a smooth surface containing these curves, you look at the corresponding surface here, and you restrict the exceptional divisor, you will get exactly these CIs. And if you pull back the hyperplane class from W, you'll get this thing. So what you have is you have codimension 2 cycles here, which restrict to what you're interested in on all these surfaces. If you assume that there is a linear relation, it's not necessarily true that you have that linear relation between these cycles on S. It just means that that linear combination, you can express it also, everything modulo, as a cycle, a vertical cycle with respect to this projection. Okay, so let me just say, so these will be the codimension J, the subgroup of the codimension J cycles on S generated by irreducible closed integral subvarieties here, with the property that when you push them forward, you get something. When you take the image for Q, you get something of strictly lower dimension. So this is the group generated by Z. Such that Q of Z, the dimension of Q of Z, okay, so you can call them the vertical classes. Okay.
It's not just the kernel of Q lower star, is it?
I mean, it's contained.
It's contained in the kernel.
Yes. Certainly, yeah.
Oh, there might be something in the kernel of Q lower star that's not. Yeah.
A priori, I guess so. Yes. Okay. So what does the spreading principle will tell me that so choose a Q is a quadratic polynomial. Okay. So we are assuming that there is some relation between these, and so we're saying if I give myself that, then Q of H restricted to, well, Q of whatever, yeah, H, and C1 of OX, C1, etc. holds for all, or even just the very general smooth x of degree d vanishing on C, if and only if we have that, what should I, yeah, if the corresponding class here is a vertical class, okay, it's in vert 2, okay. So these are exceptional devices correspond to these and this. So is in okay. Now I want to talk about modified diagonals, so I'll sort of be quick now. So now you want to prove that with these hypotheses, what do you want to prove? You want to prove that the only quadratic relations that we get are the quadratic relations that we get are linear combinations of this relation here. Well, you put the various indices. Okay? So pardon? But that's, yeah, no, of course, yes. Okay. The only relations are ci dot cj is equal to 0 if the indices are different. These are disjoint curves. And these relations here. Yes. Okay.
Can I just have one question? So at the end of the day, you're going to produce a surface in P3 or in W? Or are you going to
well, if the generic surface here will be smooth on C. So since it contains C and it's smooth on C, when you blow it up, it's
still going to be the same thing.
Yes, it will be isomorphic.
Take a surface in W and move it. What do you mean smooth on?
No, it has to. These are surfaces which contain these n curves.
Yeah. Oh, but they're So in P3 you can put it there.
Yes.
Okay.
Okay, so prove that if this holds, if star holds, then Q is in the linear span of these things here, right? Whatever I called it. X squared minus there's a here something, and then minus d x, and then also of course there's the okay. So what's the So what do you do? So it's pretty straightforward. So first of all, the Chow group of the total surface, since it's the projectivization of a vector bundle on W, you can just write as the pullback of the Chow group of W, and plus you have the first Chern class of the vector bundle. Okay, and okay, so now you have to do two things. You sort of have to, first of all, you have to see what is this group, okay, and then you have to worry about things which are 0. I mean, you could have something which is non-zero here, and when you pull it back is 0. So the kernel, so to ensure that the kernel is 0, that is that condition that I excluded about the canonical of each curve not being the restriction of the divisor. So that guarantees that if this pullback is 0, then also this is 0. When you have that condition, you get exactly a class which pullbacks. So now you have to see how large is this. And so what you see is, first of all, there's a nice class here which is responsible for this relation. So 1 if P upper star of Q is 0, then Q 0. And now what is vertical 2 of S, which is what? Yeah. Now, so there is a class that exists theta j in S of codimension 2, responsible for the relation, degree of Ci, or maybe let's call it Ci, equal to d times h. What am I doing? Yes? Ci. So what is this class? Well, this is simply, you look at, so if you want to say it briefly, you look at surfaces containing C in P3 which are singular along Ci, and each of these, when you blow them up, the surface will not be isomorphic to that. There will be typically a P1 over the singular point at the curve. And now, so the locus of these surfaces has codimension 1 in your linear system, and for each of these surfaces you have to pick a point to give yourself, and so you pick any point on that line which has replaced the singular point, and that's the codimension 2 thing. So let's say X S, where so pi of S singular at some point of Ci. At some point, let's call it Z. Okay, and X is in the symmetry. Okay, so this is codimension 2. And this is responsible. So this will be a vertical class, okay, because you see this P1 of fiber of the map. So this is vertical. And this is responsible for the relation, okay, for this relation. Yeah. Okay. And now, so what you want to say is that essentially you can get no other non-trivial vertical classes. So, but now here you have to, so to do this, you have to use another Lefschetz result on these surfaces. So you want to, so if you know that the generic that the very general surface here has Picard group generated by the obvious classes, then you're done, because sort of the difference is simply from these X to here. Here you have this extra class. Otherwise. So you take, so let me try and say it briefly. So I have an irreducible codimension 2 thing here, and which is vertical. So if the fiber here, if the image is a point, then it is just the pullback of the hyperplane here. Well, I didn't explain here, but so then it's trivial. It doesn't give any contribution to that thing there. If the generic fiber has dimension 1, then assume that the generic surface here that the image of the generic surface parameterized by this codimension 1 subset here is smooth. Is smooth in P3. Then by this Noether-Lefschetz statement that I haven't stated, the Picard of that thing, the very general surface in that codimension 1 locus here has Picard generated by the hyperplane class. So that means that the curve here, which is the fiber, is just a multiple of the hyperplane class. And pardon? Yes, plus the curves. Yes, and so that will not give you anything. I mean, I didn't talk about this side, so to get something interesting here. Okay, the only differences are these surfaces, which are the image this theta j, because here it's singular and pick of that is rank 1, but here it's rank 2. So that gives you the difference, and that's how you get the only. I mean, it's a bit confused, I realize, but. I wanted to give to say a few words about the next words in the title. Okay. Which has a relation with this, of course. Okay. So now, assuming this is more or less has been more or less comprehensible, not totally. Let's get to modified diagonals. Okay, so I'll set up some notation, otherwise, so it will be a bit nasty. So let's say something. Yes, I mean I said it quickly. Yeah, I mean the okay, the Noether-Lefschetz I stated incorrectly. Yeah. So what I need, the Noether-Lefschetz that I need is that if I have any codimension 1 subset of the smooth surfaces here, the very general member has Picard, of course, generated by H and C1 up to Cn. That's what I mean. Okay, that's the Noether-Lefschetz statement. Okay, so now let's so now we take, of course, it's not a surface, any variety, and so let's say smooth. I mean, some parts are general. So let me introduce some notation. So I want to say what are these modified diagonals. Okay, so I'll choose an index set. Okay, a subset of 1 to m. And I want some notation for the projection from. So this modified diagonal will be a cycle on the mth power of x. So I need some notation, and for the projection determined by this subset of the indices. Yes, this is the small diagonal. Okay, and I want to choose a zero cycle of modulo rational equivalence of degree 1. Otherwise, one has to rescale the definition, what I write next. Okay, and so I think this is maybe I need one other. So maybe I should just write it out. Yes, since I'm not doing any computations, I should just write it out. Okay. Yes. So I'll write some complicated cycle. So this will be, I want a cycle on x to the m whose dimension is the. So the first piece will be just a small diagonal. Okay, but so I want, okay, So I want to look at all subset of 1 to m, and then I want this -1 to the m minus. And then what do I get? I get, hope this is right. So I want to get the small diagonal of x. So I project for each such subset of the indices, not empty. I project to, I take this projection, I pull back the small diagonal here, and then I intersect with, then I project to the complementary set, and I pull back A cross A cross A. Of course, this is, okay, the proper number of times. Okay, so you start with the small diagonal, and then you go on, you know, things like A cross, etc. Okay, and if x is a point, just okay, set equals to 0. Okay. So this is the modified diagonal. Okay. So why this? So now I'll go back to so now I'll go back to Beauville and Voisin's theorem, because in proving, how do they prove this second result? They prove that if x, now it's a projective K3, then this third modified diagonal associated to that special point is 0. Okay? So this, okay. Now, so this gives you another proof of 1, although maybe it's not independent. Anyway, if you look at this equality, you see that you will get 1, but then you'll also get C2 by pulling back the diagonal from the projection to the first two factors and then pushing it forward to the third factor. So it implies 1 and 2 up here. Okay. So now maybe it's interesting to look at these modified diagonals more in general, and so let's make a simple remark. So now let's assume X smooth projective of dimension n. Okay. If there exists, of course, as I said before, degree of such that this where n, this is 1 plus the dimension of x, then for any choice of n divisors on x, you have that the intersection of these n divisors is a multiple of this special class. So what you do is you take these n divisors, you pull them back from the first n projections, you intersect them with this class which is 0, and you push them forward to the last term, and when you push forward, you will get exactly this minus this. And so you get that is 0. Okay?
Like to get 2, is the basic thing just like the self-intersection of the diagonal?
Yes.
It's the regular diagonal, usually in x plus x.
No, I think you have to project to the state, choose two factors, the first two factors.
Yeah.
pull back the diagonal from the first two factors,
Yeah.
right? I think.
But
And then you intersect with that is 0, but then you look at you project to the third factor.
But I'm just asking you a way more basic question. Just the connection to C2 at all. It's just that C2 is equal to
Right,
X.
right.
That's the usual
Right.
diagonal.
Right. Yes. Yes.
Once you
In
know-
x
yeah,
cos x.
in
Yes.
X cos X. And then all the rest, like, because that formula for the diagonal, gamma 3 is kind of.
Yes. It's sort of unpleasant at first sight. Yes.
So
Yes.
I mean, once I.
Okay. Yes. 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 That's the reason. Yes. Okay. So. So we have this implication, but we can make a remark that the other implication does not hold. Okay? Remark. So this, I don't know, A implies B, but not vice versa. You can just, I mean, it's clear it shouldn't be, but B does not necessarily imply A, so you just use the result that I tried to explain before. You look at surfaces of degree D. So outside a countable set of proper closed subvarieties, pick is Z. So this property is trivially verified. But then, so if this holds, this will be a fraction of the hyperplane class. So you can ask for all surfaces of degree D, does this hold or not? And those for which it holds, it's a countable union of closed subsets, and it can't be all of them because for those that I was talking about before, it's not true. So those for which it holds is a countable union of proper closed things. And so outside of those, you have those, some of them will have pick Z for which this holds. So I don't know if I mixed up your ideas. But anyway, this does not hold. Okay? So A is actually stronger. So, well, I'll finish with this conjecture because I'm sort of wasted my time. So let's say X is a hyperkaehler variety. Yeah, because say so if this has to hold for some surface in P3, this has to be if it's degree D, this A has to be 1 over D times H squared. So this is a zero cycle which is defined for all surfaces of degree D, and so this is a class you can define on all surfaces. You can put it in the family of all surfaces. Yeah. So you have a codimension 2 cycle on the family of all surfaces. So the members of this family for which that is rational equivalent to 0 is a countable union of closed subsets. Yes, yes, that's the, yeah. Yes. Yeah. So demanding that a cycle is rationally equivalent to 0. Yeah. Not really a priori closed condition. No, it's a countable union of closed things. Yeah. So it's the union of countable. So it could be. It's not. It will not be closed in the Zariski, but it will be a countable union of closed things. And what I proved before is that it's not true for all x's because you have those x's for which the group of decomposable cycles has rank bigger than 1. Yeah. And if this holds, it has rank 1. Oh, I see the countable union just because any relation. Yeah. Okay, it's the kind of, you have. Yeah, I get okay. Yeah. So let me write this, then I can tell you later. Yeah. So X, a hyperkaehler variety of dimension 2n, there exists a zero cycle class of degree 1 such that okay, So, of course, in dimension 2, this is exactly Beauville and Voisin's result. This is the same as the dimension. I'm just stressing that the dimension of a hyperkaehler variety is even. That's all. Okay, so maybe I should stop because there's another talk. And I shouldn't. Yes.